Today we're going to explore one of the most fascinating phenomena in microfluidics, inertial focusing. This is where particles or cells spontaneously migrate to specific equilibrium positions within a microchannel due to finite inertial effects at intermediate Reynolds numbers. To understand inertial focusing, we first need to understand what happens at very low Reynolds numbers. In traditional microfluidics, we usually work in the Stokes flow regime, where viscous forces completely dominate over inertial forces. The Reynolds number equals density times velocity times hydraulic diameter divided by viscosity. This dimensionless number tells us the ratio of inertial to viscous forces. When the Reynolds number is much less than 1, viscous forces dominate completely. In this regime, particles simply follow the fluid streamlines with no cross-stream migration. Here's what Stokes flow looks like in a channel. The flow is perfectly laminar, and particles at different heights maintain their vertical positions. They just flow along with the fluid. But here's the key question. What happens when we increase the flow rate and push into the intermediate Reynolds number regime? This is where the magic of inertial focusing begins. In the intermediate Reynolds number regime, typically between 1 and 100, something remarkable happens. Inertial effects become significant, but not dominant. We're talking about Reynolds numbers between 1 and 100. This is the sweet spot for inertial focusing. Now particles migrate across streamlines to specific equilibrium positions. Those green arrows show the lateral migration. Particles that start at random positions all move toward these equilibrium points. Inertial focusing arises from the delicate balance between two competing inertial lift forces. Let me explain each one carefully. The first force is the shear-gradient lift force. This force arises because of the parabolic velocity profile in the channel. The shear-gradient lift force scales as density times velocity squared times particle diameter to the fourth power divided by channel diameter squared. This force pushes particles away from the channel center toward the walls. Why? Because the velocity gradient is steepest near the center line, where the flow profile curves the most. Here's a particle at the channel center experiencing the shear gradient force. It gets pushed both upward and downward away from the center line. The second force is the wall-induced lift force. This one arises from the interaction between the particle and the nearby channel wall. The wall lift force scales as density times velocity squared times particle diameter to the sixth power divided by channel diameter cubed. This force pushes particles away from the walls toward the channel center. It's caused by the asymmetry in the flow field around a particle near a wall. Here's a particle near the wall. The wall-induced lift force pushes it away from the wall toward the center. So we have two opposing forces. The shear gradient pushes away from center, the wall lift pushes away from walls. Where do they balance? Here's the key insight. Notice the different scaling laws. The shear gradient goes as particle diameter to the fourth power, but wall lift goes as the sixth power. This means the wall lift force dominates when you're very close to the walls. But the shear gradient lift dominates in the channel interior. The balance between these forces creates equilibrium positions. For a square channel, you typically get 4 equilibrium positions centered on each face. For a rectangular channel, you get 2 positions on the wider faces. Let me ask you a key question. Why does inertial focusing only work at intermediate Reynolds numbers? Why not at very high or very low Reynolds numbers? The answer is that both lift forces scale with the Reynolds number. They're both inertial effects. At very low Reynolds number, both forces are negligible and particles just follow streamlines. At very high Reynolds numbers, above a few hundred, the flow transitions to turbulence. The chaotic fluctuations destroy the stable equilibrium positions. Let's do a back-of-the-envelope calculation to understand the relevant length and timescales. This will make the physics more concrete. Let's consider 10 micrometer diameter particles flowing in a 50 micrometer square microchannel. This is a typical size for blood cells or microbeads. So particle diameter A equals 10 micrometers, hydraulic diameter DH equals 50 micrometers. We're flowing water with density 1,000 kilograms per cubic meter and dynamic viscosity 0.001 Pascal seconds. Let's target a Reynolds number of 50, right in the middle of the focusing regime. Reynolds number equals 50 equals 1,000 times U times 50 times 10 to the minus 6 divided by 0.001. Solving for U, we get approximately 1 meter per second. That's a pretty fast flow for microfluidics. Now let's estimate how long the channel needs to be for particles to reach their equilibrium positions. This is called the focusing length. The focusing length scales as channel diameter cubed divided by density times velocity times particle diameter squared, all times the Reynolds number. This formula captures the fact that lateral migration is much slower than the main axial flow. Particles need time to migrate to equilibrium. Plugging in our numbers. 50 times 10 to the minus 6 cubed divided by 1,000 times 1 times 10 times 10 to the minus 6 squared times 50. This gives us a focusing length of approximately 6 millimeters, so we need a channel several millimeters long for complete focusing. Now let me address an important practical consideration. Channel geometry matters tremendously for inertial focusing. In a square channel, you get 4 equilibrium positions located near the center of each face, slightly offset from the walls. Here's the cross-section of a square channel showing the 4 equilibrium positions. They're symmetrically arranged. In a rectangular channel with aspect ratio greater than about 2, you only get 2 equilibrium positions on the longer faces. Here's a rectangular channel. Notice we only have 2 equilibrium positions on the wider top and bottom faces. This is often preferred for single-line focusing. If you curve or spiral the channel, you introduce additional centrifugal forces that create secondary flows called Dean flows. These can be used to enhance or modify the focusing behavior. You might be wondering, why do we care about inertial focusing? What are the practical applications? Let me give you several important examples. First, high-throughput flow cytometry. By focusing cells into a single stream, you can interrogate them one by one with lasers or imaging systems at very high rates, up to thousands of cells per second. Second, size-based cell sorting. Because the equilibrium position depends on particle size, different sized particles focus at different positions. You can exploit this for label-free separation. The equilibrium position scales approximately as particle diameter squared, so larger particles focus closer to the center line than smaller particles. Third, particle concentration. You can use inertial focusing to concentrate dilute particle suspensions into tight streams, which is useful for downstream processing. Fourth, sample preparation for medical diagnostics. Inertial focusing can isolate rare cells like circulating tumor cells from blood samples. Let me dive deeper into the size dependence, because this is absolutely critical for understanding and designing inertial focusing devices. The net lift force scales as particle diameter to the 4th power. This is a very strong size dependence. This strong size dependence means inertial focusing works best for relatively large particles or cells, typically above a few micrometers in diameter. Here's another important question. What is the minimum particle size for effective inertial focusing? The answer depends on your channel dimensions and flow conditions, but generally you need the particle confinement ratio, which is particle diameter divided by channel diameter, to be at least 0.07. The ratio A over dH should be greater than about 0.07. Below this, the lift forces become too weak compared to diffusion. For very small particles, Brownian motion becomes significant and can disrupt the focusing. You need the inertial migration to be faster than diffusive spreading. Let me briefly discuss an advanced topic. Secondary flows and Dean vortices in curved channels. This adds another layer of physics. When you bend a channel, centrifugal forces create secondary flows perpendicular to the main flow direction. The strength is characterized by the Dean number. The Dean number equals Reynolds number times the square root of hydraulic diameter divided by twice the radius of curvature. Here's a representation of Dean vortices. The blue arrows show the main flow around the curve, while the green arrows show the secondary vortex flow. These vortices can enhance mixing and modify particle trajectories. By carefully designing curved channels, you can combine inertial lift forces with Dean drag forces to achieve more sophisticated particle manipulation and separation. Now let's talk about some practical, experimental considerations and challenges when implementing inertial focusing. First, channel fabrication precision. The equilibrium positions are sensitive to channel dimensions. You need tight tolerances, typically within a few micrometers, to get reproducible focusing. Second, particle clogging. At high particle concentrations, particles can aggregate and clog the channel. You need to optimize the concentration, typically below 1% volume fraction. Third, flow stability. Pressure-driven flow must be steady. Pulsations from syringe pumps can disrupt focusing. You may need dampeners or pressure regulators. Fourth, entrance effects. The flow needs to be fully developed before focusing occurs effectively. You need an entrance length of roughly the focusing length we calculated earlier. How does inertial focusing compare to other particle focusing methods? Let's put this in context. Hydrodynamic focusing uses sheath flows from multiple inlets to squeeze particles into a narrow stream. It's simple, but requires careful flow rate control and multiple pumps. Acoustic focusing uses ultrasound standing waves. It works well for smaller particles, but requires piezoelectric transducers and careful acoustic design. Dielectrophoretic focusing uses electric field gradients. It's powerful, but requires fabricating electrodes and applying high voltages. Inertial focusing is passive, requiring no external fields or multiple inlets. It's simple, robust, and capable of very high throughput. The main limitation is the size requirement and Reynolds number constraints. How do we quantify how well the focusing is working? Let's discuss some metrics. Focusing efficiency is the percentage of particles that reach the equilibrium positions. Good focusing typically achieves above 90% efficiency. Focusing width measures the spread of particle positions around the equilibrium point. Tighter focusing means narrower distribution, typically quantified by standard deviation. For good focusing, the standard deviation of particle positions should be less than about 10% of the channel dimension. Throughput is the number of particles processed per second. Inertial focusing can handle very high throughput, up to millions of particles per second. Let me conclude by discussing some recent advances and future directions in inertial focusing research. Researchers are developing complex three-dimensional channel geometries to achieve more precise control over equilibrium positions in all three dimensions. There's exciting work combining inertial focusing with other forces like viscoelastic effects, magnetic forces, or optical forces to enable more sophisticated separations. Viscoelastic focusing uses elastic stresses in polymer solutions to focus particles. This can work for much smaller particles, even down to nanometer scales. Machine learning is being applied to optimize channel designs. Neural networks can predict focusing behavior and suggest optimal geometries for specific applications. Let me summarize the key physics principles we've covered about inertial focusing. At intermediate Reynolds numbers between 1 and 100, finite inertia creates lateral lift forces that cannot be neglected. The balance between shear gradient lift and wall-induced lift determines equilibrium positions. These forces scale differently with distance from walls. The lift force has a very strong size dependence, scaling as particle diameter to the fourth power. This enables size-based separations. Channel cross-sectional geometry determines the number and location of equilibrium positions. Square channels give 4 positions. Rectangular channels typically give 2. The focusing length, the distance needed for particles to reach equilibrium, scales as channel diameter cubed and increases with Reynolds number. Applications range from high-throughput flow cytometry and cell sorting to sample preparation for diagnostics and materials processing.